Hi there, welcome to the second video on the further calculus topic, looking at using the chain rule and using the chain rule to differentiate composite functions. Okay, now with the success criteria, I'm not going to spend too much time on them yet because I want to introduce it to you first. Okay, but they're there, we'll revisit them at the end. Okay, so just a wee reminder, I want you to pause the video and differentiate this function. Okay, so y is equal to 2x plus 5 cubed. Okay, now if you've done that, what you would have done is multiply out the bracket. So if we do 2x plus 5 cubed means 2x plus 5 times 2x plus 5 squared. So that'll be 4x squared plus 20x plus 25. And then multiply out that bracket to give you this. Okay, so multiplying out, you get 8x cubed plus 60x squared plus 150x plus 125. So I just skipped ahead here just to save a bit of time on the video. So when you can now go and differentiate that, that gives you 24x squared plus 120x plus 150. Okay, now I'm hoping you can see, obviously I skipped a wee bit, so didn't illustrate it fully, but you can see how onerous that is, particularly if you raise that power from a cube to a power 4 or a 5 or a 6 or even a 10. That's going to be something that's an absolute nightmare to differentiate. Okay, now there is another way of doing this. Okay, and I'll show you the proof in a wee second, but okay, if you take this as a composite function instead, so instead of thinking about it as 2x plus 5 cubed, you think about it as u cubed. Okay, now we are still wanting to find dy by dx. Okay, now we want to find dy by dx, we've got that function u in there. We can do that by doing differentiating y with respect to u, and then multiplying it by the differential of u itself with respect to x. Now what will happen there, just a simple multiplication with your fractions, your du will cancel out and leave you with your dy by dx. Okay, so dy by dx here is going to be differentiating, firstly, u cubed, just in terms of u. So it'll be 3u squared. And then we're going to multiply d by du by dx. Now in this case, u is equal to 2x plus 5. So when you differentiate that with respect to x, all that happens is your 2x just becomes a 2. So we're going to multiply it by 2. Okay, so dy by dx here is 6u squared, okay, which means 6 times 2x plus 5 squared. Okay, now I'm just going to give myself a little bit more room here. That's 6 times 4x squared plus 20x plus 25. And when you times that through by 6, you can see it's 24x squared plus 120x plus 150. Okay, now this here is the theory. Okay, when you want to find dy by dx when you've got a composite function, you essentially ignore the bracket first of all and differentiate, and then you multiply it by the differential of what was inside that bracket. Okay, now you don't need to worry about setting out like this. Okay, you can just do it practically. As long as you can do the process, that's fine. So actually what we're looking at, that's your, this here is your proof, but this is what you're actually going to do. Okay, differentiate the bracket, ignoring what's inside, and then go back and multiply it by the differential of inside the bracket. Okay, and if you look back at the success criteria, that's essentially what that was, with a bit more simplification in there. Okay, so this one here, first thing we're going to do is we're just going to ignore that bracket. Okay, we're just going to ignore what's there. Okay, so you've got y equals something to the power 6. Okay, so your differential, firstly, ignoring the bracket, is that bracket there, whatever it is, times by 6 at the start, and decrease your power by 1, just like you would normally in differentiation. Okay, now the bracket's not going to change, it's still going to be 3x minus 5. Okay, but you also need to go back inside your bracket and differentiate what's there. So 3x minus 5 differentiates just to 3. Okay, so that's going to be 18 when you do the 6 times 3, 3x minus 5 to the power 5. Now you don't need to bring out the brackets, that was just to highlight in the last slide how they end up being the same. That is your differential. And look how much time we saved. Didn't have to worry about any of the power 6 stuff. We just were able to do that there. Okay, so same again here. Cover up the bracket. I don't care what's in there. Okay, don't care what's in there. We're just going to differentiate ignoring that first of all. Okay, so dy by dx, the 4 comes down, the bracket is going to stay the same and it becomes cubed. Okay, so then the bracket just stays exactly the same. It's 5x cubed minus 2x. but then we're going to times it by the differential of what's inside there. Now it's going to be a little bit messier, it's not going to be as pretty. That's going to be 15x squared minus 2 getting multiplied there. Okay, there's no simplification to be done. There, the 6 times 3 was nice and easy. You don't need to worry about anything there. That is your differential. Okay, I'm going to do a couple more examples. Okay, firstly, y is equal to 3 over 2x minus 1 squared. Okay, so same again, to differentiate, we know we need that fraction up. This time the whole bracket moves and becomes a negative 2. Okay, then we're ready to differentiate. Cover up what's inside the bracket, ignore what's there. Okay, this time we're going to do minus 2 coming down. So dy by dx is minus 2 times 3 is minus 6 times the bracket, which stays exactly the same. Oops. Sorry about that. Bracket stays exactly the same. 2x minus 1, this time to the power negative 3. And then go back into your bracket and differentiate what's there. That's times by 2. So the differential is minus 12 times 2x minus 1 to the power negative 3. Okay, so it could be minus 12 over 2x minus 1 cubed if you wanted to tidy it back up. Okay, this one here, I hope you can see straight away what's wrong. Give it a try, pause it. Okay, but this needs to turn in to a bracket. Because it's a square root, it's a power 1 over 2. Okay, then we're good to go. Dy by dx. Cover up what's inside the bracket. Okay. Cover up what's inside the bracket. Don't care what's there. Your half comes down. Your bracket is going to stay the same, and it's minus a half. Excuse me, sorry. Oh, done it again. Okay, so your bracket's going to stay as 4x minus 5. You then go back into your bracket and differentiate what's there. In this case, that'll give you a 4. And then you can just tidy up. So half times 4 will be 2 times that bracket. Okay, and if you wanted to do it properly rearranged, the negative will send it to the bottom and the half will turn back into a square root. Okay, so that's your differential there. And you can see how really that one there and this one here, they're not able to be done even by multiplying out the bracket. So we need this in order to be able to differentiate. Okay, now the last time we're going to look at is a couple of trigonometric terms. Okay, and these ones are particularly tricky. The SQA love examining these because they are tricky, but another example being where you have to use this chain rule. Okay, and the reason they are so tricky is because the brackets are hidden. Okay, so y equals sine 2x. We know that really means y equals sine of all of 2x. So there's a bracket there that we can't see. And if it helps, write it again with a bracket in. Okay, now we're ready to differentiate. Okay, so to differentiate, to get dy by dx, firstly we're going to cover up the bracket. Okay, we cover up that 2x. Excuse me, sorry. Cover that 2x and ignore what's in there. So we're doing sine of something. Okay, now the common mistake a lot of kids like to make is the fact that they're looking for powers. You don't have powers here, you've got a sine. And you know that sine differentiates to be cos. So it's going to be cos of that same bracket. Okay, so it's cos of 2x. But then you also have to go back into the bracket and times by the differential of 2x, which is 2. So the differential of sine 2x is 2 cos 2x. Okay, and that's not tricky per se, but knowing what you're doing there, knowing to use the chain rule is what makes that a trickier question. Okay, with the second example there, if we put the squared in the middle, we know that means the whole bracket, the whole sine x is squared. Okay, so when you go and cover up that bracket to differentiate, dy by dx, you're going to ignore what's in the bracket, you've got something squared. So the 2 just comes down and multiplies by sine x, the power of that becomes 1. But when you go back in the bracket this time and differentiate sine x, you know that differentiating sine x gives you a cos x. Okay, so dy by dx is equal to 2 sine x cos x. Okay, which trig enthusiasts amongst you will notice that that becomes sine 2x, but don't worry about that just now. Worry about using the chain rule. Okay, so covering up the bracket there, the 2 comes down, the power becomes 1. Going back into the bracket means you're differentiating sine x to give you cos x. Okay, and then g, very similar. And I've used sine in every case here just so you can see how similar they all look. Okay, that means that it's sine of x squared. Covering up the x squared then, again, is just going to mean your derivative is cos of x squared. But then when you go back in and differentiate your bracket, x squared becomes 2x. So dy by dx is 2x cos x squared. Okay, now going back to your success criteria, 3 things you need to be able to do. Be able to differentiate the function ignoring the bracket. Okay, being able to multiply with the differential of what's inside the bracket and then complete any simplification. Okay, you could add in here as well that actually the 4th thing we could do is cope with trigonometric terms as well, or even identify when to use the chain rule with trigonometric terms. Okay, that could be a 4th one that maybe should have put in. Okay, so being able to do that, that's tricky, identifying where you have to use this, and it does come up a lot in the exams. Okay, but there is hints in the formula sheet for that. Okay, thanks for listening.